Hi, and welcome back to my series of videos for Physical Chemistry 2. For the past few videos, we've looked at some of the properties of atoms and ions, but we did it in a very qualitative way. Although we talked about the radii and ionization energies of different atoms and ions, we didn't talk about how those values can be calculated. That'll be the topic of the next few videos. Back in video 20, we saw how to use determinants to evaluate the wave function of an atom. And before that, we thoroughly looked at the hydrogen atom and how to solve its Schrodinger equation. So you might think we should be able to solve for larger atoms in the same way, right? Well, unfortunately not. When we try to solve the Schrodinger equation for other atoms, including atoms as small as helium, we find out that there's a problem. As you know, helium contains 3 particles, the nucleus and 2 electrons. Since it has a positive charge, the nucleus attracts both electrons, and because the electrons both have a negative charge, the electrons repel one another. In order to determine the energy of the atom, we need to determine the average distance between each of those particles. In physics, this is known as a 3-body problem. But 3-body problems are kind of famous, because it turns out they can't be solved exactly. Why not? Well, suppose we imagine that the nucleus is located at the origin of our coordinate system. Using concepts we've already talked about, we could figure out the average distance that an electron should have from the nucleus. But there's a problem. As I mentioned a moment ago, the electrons repel each other, so they won't quite be at the distance that we just calculated. Based on their repulsion, we can adjust the positions of the electrons, but that means that they're now in a different location in the potential field generated by the nucleus. That means we'll have to reevaluate the attraction between the electrons and the nucleus. And that will result in a new separation between the nucleus and the electrons, which means we now have to recalculate the repulsion between the 2 electrons. And that causes yet another adjustment in their positions. This could continue forever. Every time we recalculate the electrons' attraction to the nucleus, their positions change. So we have to recalculate the repulsion, which also makes their position change, over and over and over in an endless loop. Each time we go through one of those cycles, the adjustment we have to make to the positions becomes a little bit smaller. So those positions asymptotically approach their real value, but they never quite get there. So that means we can only ever find the exact positions of the particles in the system if there are only 2 particles, the nucleus and 1 electron. In other words, a hydrogen atom. We can only approximate the positions of the particles for any system larger than hydrogen. But those positions are crucial to our ability to calculate properties like the ionization energy and the radius of the atom. So, does that mean we're at a dead end and there's nothing else we can learn from quantum mechanics? No. It just means that from now on, we'll have to be content with only approximating the positions of the particles, the energy of the system, and the expression for the wave function. But as we'll see, the approximations we make are often very, very close to the true value, so they still yield results that we can feel confident about. So, how do we make those approximations? Well, we'll go into greater detail in future videos, but for now I'll give you a brief overview. Suppose we have a system with more than 1 electron, and we want to know its energy. As you might remember, we determined the energy by solving the Schrodinger equation for the system. The Schrodinger equation has this form, where H is the Hamiltonian operator. In this case, because there are multiple interacting electrons, we don't know the exact form of the wave function. But if we want to know the exact energy, we need to know the exact form of the wave function. Since we only have an approximation to psi, the energy will necessarily be incorrect. The better the approximation of psi, the closer the energy we calculate will be to the true value. So we really want that approximate wave function to be as good as we can make it. Let's rewrite the Schrodinger equation slightly so that we emphasize the fact that the wave function we're using isn't the exact one. In this equation, phi is called the trial wave function, and E with the subscript phi is the energy we'll get when we use that trial wave function to calculate energy. It turns out that E phi is always guaranteed to be higher than the real ground state energy. This important concept is known as the variational principle. As I mentioned, the better our trial wave function, the closer E phi will be to the true energy. It'll still be higher than the real energy, but it could be very, very close if our trial wave function is especially good. So, what should we use for the trial wave function? Well, you might remember from video 18 that the Hamiltonian for a helium atom is very similar to the sum of the Hamiltonians of two different hydrogen atoms, plus an additional term to account for the repulsion between the electrons. That gives us a clue as to what might make a good trial wave function. Since the first group of terms in the Hamiltonian for a large atom containing n electrons is just like a sum of Hamiltonians for n different hydrogen atoms, maybe a good trial wave function would be the product of different hydrogen wave functions, one for each electron. For example, if we have a helium atom, our trial wave function could be this, where each hydrogen wave function is for a 1s electron, since we know that's what the electrons are in a helium atom. If we had a larger atom, like carbon, some of the hydrogen wave functions in our trial wave function would be for higher orbitals, like 2s or 2p. Now, if we want to calculate the energy of the system, we'd use this integral, which we've seen before. Remember, the expectation value of a property like the energy is calculated by taking the integral of phi star phi with the operator for the property in between the two wave functions. Since the operator for energy is the Hamiltonian, that's the operator in the middle of the integral in this case. So, to calculate the energy, we need to insert our expressions for phi and h, and then solve the integral. That's a very tedious calculation. Almost no one would actually solve an integral like that by hand anymore. Instead, there are many computational software packages that can do it for us. When we do solve it for our helium, we find that the energy is given by this expression. Notice that the first group of numbers is all constants. In fact, it's the same group of constants that we saw when we talked about atomic units back in video 18. So these constants are equal to 1 Hartree, or 4.3597 times 10 to the minus 18 joules. So, what's the energy? Well, remember that the variational principle tells us that the energy we calculate this way is always going to be higher than the true energy. So, to get the most accurate energy we can, we want the energy we calculate here to be as low as possible using this equation. You might think that we could get the minimum by having z be equal to 0, which would give us 0 for the energy. But actually that isn't true. The energy of an atom is usually a negative number, so 0 is definitely not the lowest energy we could get. Instead, you might remember from your calculus course that you can find the minimum of a function by taking its derivative and setting the derivative equal to 0. In other words, for this function, we want the derivative of e with respect to z to be equal to 0. The derivative of e with respect to z is this. When we set that equal to 0, we find out that the value of z must be 27 over 16. So, now that we know z, we can plug that into the equation for energy. When we do, we find that it gives us an energy of negative 1.2415 times 10 to the minus 17 joules. How close is that to reality? Well, if we actually measure the energy of a helium atom, we find out that it's negative 1.2658 times 10 to the minus 17 joules. Notice that the energy we calculated is slightly higher than the true value. That's exactly what the variational principle tells us should happen. But even though our calculated value is slightly wrong, it's still pretty close. We have an error of just under 2%. But why is there any error at all? Well, remember we got this equation for the energy by starting with a trial wave function, not the real wave function, which we don't know. Is it possible for us to improve the trial wave function so that the value we get for the energy is a little more accurate? The answer is yes. And we'll talk more about the way we improve our trial wave function in a future video. But that's enough new material for now. When we meet again, we'll talk about that variable z we used in the energy equation. You might have realized that z is the symbol we use for the charge on the nucleus. In other words, it's the atomic number. But then, why did we get a fraction instead of an integer for z? To find out, I hope you'll join me in the next video. But until then, have a good week.